In the gleaming terminals of modern airports, passengers board aircraft powered by the same fundamental technology their grandparents flew on 60 years ago: jet engines that burn fuel, generate thrust, and leave contrails across the sky. But locked away in research facilities and buried in patent archives sits a different kind of propulsion system, one that major airlines have quietly tested. Aviation engineers have reluctantly praised, and corporate boardrooms have systematically ignored for decades. The technology works, the prototypes have flown, and the efficiency gains are undeniable. Yet somehow this revolution in aviation has remained perpetually grounded, always 5 years away from transforming an industry that seems increasingly determined to ensure it never arrives: the ghost in the hangar. The ghost in the hangar isn't a legend or a rumor, it's a fully functional aircraft sitting in a research facility, looking like it arrived from a future that somehow got here ahead of schedule. The engineers who work around it speak in hushed tones, careful about what they say and to whom, because what this machine represents could fundamentally disrupt an industry worth hundreds of billions of dollars. At first glance, it doesn't look revolutionary at all. The fuselage seems conventional enough, the wings appear familiar, but then the details start revealing themselves. The propulsion system is entirely different from anything currently flying commercial routes. The control surfaces move in ways that seem almost organic, and the performance numbers, the ones that get whispered about in technical conferences and then quickly dismissed, suggest capabilities that would make current airliners look like they were designed with slide rulers for an era that disappeared generations ago. Well, that's not even the strangest part. This technology has been demonstrated multiple times over the past several decades, proven in wind tunnels and test flights, validated by physics that nobody disputes. And yet it never made it to production, never showed up on commercial aircraft, never transformed the industry the way it should have. Instead, it kept appearing in prototype form, generating excitement and technical papers, and then vanishing back into research programs that seemed to go nowhere. The question hanging over that hangar isn't whether this technology works. Everyone involved knows it does. The mystery is why something so promising, so thoroughly validated, kept getting buried by an industry that claims to be constantly seeking innovation. Because every time this ghost appeared, powerful forces seemed determined to make it disappear again. And understanding why requires looking at the economics and politics that govern aviation in ways most passengers never imagined. The Forbidden Blueprint. The Forbidden Blueprint emerged from the drawing boards of aerospace engineers in the 1970s, a period when aviation was experiencing unprecedented growth and fuel prices were forcing the industry to rethink everything it thought it knew about efficient flight. The concept was elegant, almost obvious in hindsight, and the initial calculations suggested it could reduce fuel consumption by margins that seemed too good to be true. Except they weren't too good to be true. Early wind tunnel tests confirmed what the mathematics predicted. Prototype systems demonstrated the principles in controlled environments. And by the early 1980s, several major aerospace companies had invested significant resources into developing this technology for commercial applications, convinced they were looking at the future of aviation. Then something extraordinary happened. Or rather, something extraordinary didn't happen. Despite the promising results, despite the validated physics, despite the potential for massive fuel savings at a time when every airline was desperate to reduce operating costs, the project started getting quietly shelved. Funding dried up, research teams were reassigned, and the blueprints that should have revolutionized commercial aviation got filed away in corporate archives, treated like classified documents from a program that never officially existed. Well, that's not even the most puzzling part of this story. Some of those engineers kept working on the technology anyway, publishing papers in academic journals, presenting at conferences, keeping the concept alive even as the industry seemed determined to ignore it. They built smaller prototypes, demonstrated the principles over and over, and watched as each new validation was met with the same corporate indifference that had buried the original projects. The reasons for this suppression weren't hidden in some conspiracy. They were sitting right there in plain sight for anyone willing to look. Implementing this technology would have required retooling manufacturing facilities built for conventional designs. It would have made existing fleets obsolete decades before their planned retirement. And it would have disrupted supply chains and maintenance programs that represented billions of dollars in established infrastructure, built by companies and airlines that had no interest in seeing their investments become worthless overnight. So the blueprint remained forbidden, not by law or regulation, but by an industry that had too much invested in the old way of doing things to embrace a future that arrived inconveniently early. The physics they don't want you to know, the physics they don't want widely understood, aren't actually secret at all. They're taught in aerospace engineering programs and published in textbooks that anyone can access. But understanding why these principles matter, why they represent such a fundamental threat to conventional aviation, requires looking at how aircraft have been designed for nearly a century and recognizing that almost everything about that approach could be done differently. Conventional aircraft generate lift by forcing air over curved wing surfaces, a principle that works remarkably well but comes with inherent inefficiencies that have been accepted as unavoidable since the Wright brothers first took flight. The revolutionary technology exploits a completely different aerodynamic phenomenon, one that generates thrust and lift through mechanisms that seem almost counterintuitive until the mathematics reveal why they work so elegantly. The breakthrough involves manipulating airflow in ways that reduce drag by margins that sound impossible to engineers trained in traditional methods, where conventional designs fight against physics, accepting energy losses as the price of flight. This approach works with aerodynamic principles that have always existed but were considered too complex or impractical to implement at commercial scale. Well, that's not even the most remarkable aspect of these physics. The efficiency gains aren't incremental improvements measured in single percentage points. They represent paradigm-shifting reductions in fuel consumption that would fundamentally alter the economics of air travel. Aircraft built on these principles could fly the same routes as current airliners while burning a fraction of the fuel, or travel significantly farther on the same amount of energy. And here's what makes this so threatening to established aviation. The physics don't require exotic materials or technologies that don't exist yet. Everything needed to build these aircraft has been available for decades, sitting on shelves and in catalogs, waiting for an industry willing to abandon designs that have defined commercial aviation since jet engines replaced propellers on passenger aircraft. The trillion-dollar threat. The trillion-dollar threat isn't a figure of speech. It's a conservative estimate of the combined value that would evaporate if this revolutionary technology actually reached commercial production. Airlines have fleets worth hundreds of billions of dollars, aircraft designed to operate for 20 to 30 years before retirement. Manufacturing facilities have been optimized for building conventional airframes. Supply chains have been established around components and systems that would become obsolete overnight. And then there's the infrastructure, the maintenance networks, the training programs, the spare parts inventories sitting in warehouses around the world. Every major airport has hangars and equipment configured for servicing aircraft built on principles that have remained fundamentally unchanged since the jet age began. Mechanics have spent entire careers learning systems that would suddenly be irrelevant. Engineers have expertise in technologies that would no longer matter. The resistance to this innovation isn't coming from some shadowy conspiracy. It's emerging from the simple economic reality that entire sectors of the aviation industry have too much invested in the current paradigm to tolerate disruption on this scale. When Boeing or Airbus considers a new aircraft design, they're not just thinking about performance and efficiency. They're calculating the impact on production lines that cost billions to establish and supply chains that involve thousands of companies across dozens of countries. Well, that's not even the full extent of the threat. The technology doesn't just make current aircraft less competitive, it fundamentally undermines the business models that airlines and manufacturers have built over decades. Routes that are barely profitable with conventional aircraft become highly lucrative. Destinations that seemed too distant for efficient service suddenly become accessible. And the competitive advantage goes to whoever adopts the new technology first, creating pressure that makes resistance increasingly difficult to maintain. The question by the 2010s wasn't whether this disruption would happen, it was whether the industry could continue delaying it. The silent revolution. The silent revolution is happening in facilities that don't make headlines, funded by investors who understand that disruption creates opportunities that established players can't exploit. Startup aerospace companies, unburdened by legacy infrastructure and existing fleets, are building aircraft based on those forbidden blueprints from decades ago, updated with modern materials and digital systems that make the original concepts even more effective. These aren't concept drawings or theoretical proposals anymore. Flight testing is underway, certification processes have begun, and the performance data emerging from these programs is validating everything the suppressed research predicted, demonstrating fuel efficiency improvements that would have seemed like fantasy just a few years ago when the technology was still buried in corporate archives. Well, that's not even the most significant development. Major airlines watching these startups attract billions in investment and seeing the inevitable trajectory of fuel costs and environmental regulations are quietly beginning their own research programs. The same companies that spent decades ignoring this technology are now scrambling to understand it, hiring engineers who worked on those original projects and dusting off blueprints that were supposed to stay forgotten. The transformation won't happen overnight. Conventional aircraft will continue flying for years, maybe decades. But the revolution that was delayed for so long has finally begun, driven by forces that even trillion-dollar industries can no longer resist. The ghost in the hangar is becoming real, and aviation will never be the same. The sky's new rules are being written right now in design offices and testing facilities where the future of aviation is taking shape in ways that would have seemed impossible when those original blueprints were first suppressed. Passengers might board aircraft that fly farther on less fuel, opening routes that were never economically viable before. Ticket prices could drop as operating costs plummet, and the environmental impact of air travel, currently one of the fastest growing sources of carbon emissions, might finally begin declining instead of accelerating. The transformation that was delayed for decades is finally arriving, not because the industry suddenly discovered innovation, but because the economic and environmental pressures became too intense to resist any longer. That ghost in the hangar is about to become the standard against which all future aircraft are measured. And somewhere, engineers who worked on those forbidden projects decades ago are watching their suppressed innovations finally take flight, proving that good ideas don't disappear. They just wait for the world to catch up.